So now we're going to look at some periodic trends. And just like trends among human beings in the real world, the trends are useful and they help us predict things, but there are lots of exceptions to things. Like you could say that in general, as a child goes through grade school, they get taller, right? So if I ask you who's taller, the 5th grade boy or the 3rd grade boy? Probably the 5th grade boy. Are there 5th grade boys that are shorter than some of the 3rd graders? Yes, absolutely there are. There's nothing wrong with that, right? But there's a general trend. And so all of these trends are general trends. They are useful, but they also have exceptions, and we're not going to worry too much about the exceptions. So the first one we're going to talk about is atomic size, the size of the atoms. And before we can look at a trend, we have to decide, well, how do you define the size of an atom? Because an atom is not like a marble where there's a distinct edge that you can get out a ruler and measure, right? Most of the atom is taken up by these standing waves of particle electrons, right? And it's kind of fuzzy around the edges, and how do you measure that? So there's several different ways that you can define atomic size. One is called van der Waals radius, also known as a non-bonding atomic radius. And so this looks at adjacent nuclei in an atomic solid. So here we have krypton made really, really cold, so it becomes a solid. This is an atomic solid. Those atoms are not bonded to each other covalently. They're just next to each other. And we can measure the distance between two nuclei. And so then we can say, well, it's reasonable that the distance between two nuclei would be twice the radius of those atoms, right? Yes, it is assuming the nucleus is in the center, and the nucleus is in the center. Yeah. So it's a good assumption. We can also look at a bonding atomic radius, sometimes called a covalent radius, because when two atoms bond together, like we have illustrated here with bromine, this molecule, there is actually a chemical bond, a covalent bond here, and that pulls the nuclei closer than they would be if they were just sitting next to each other in an atomic solid. So this radius is going to be different. But again, we look at the distance between the nuclei, divide that by 2, and say, well, that's the atomic radius. Now that's going to be a little bit distorted perhaps, because is this radius here, which is what we're measuring, is that really the same as out here? You know, this picture makes it look like it's not really spherical anymore. It's kind of, you know, stuck to the other one, so there's indented there. We're not going to worry about it. The bonding radius is always going to be smaller than the non-bonding radius. So there's lots of different ways to measure the atomic radius, and so what we're going to look at is, we're just going to call it atomic radius, and that's an average based on lots of different types of measurements in lots of different elements and compounds. Because the radius that you get for bromine bonded with bromine is different than what you would see for bromine bonded with hydrogen. And so there's just so many possibilities, and so we're just kind of looking as a general average. We can approximate a bond length, like if we had hydrogen and bromine, we wanted to know, well, what's the bond length? What's the distance between the nuclei? We could look up the atomic radius of bromine and the atomic radius of hydrogen and add them together, and that would give us a ballpark estimate of what the bond length was. So now we can talk about trends in the atomic radius. So this is a kind of a weird looking graph. We like things that are linear, and this is absolutely not even close, right? So on the y-axis we have the radius in picometers, and on the x-axis we have atomic number. So we're starting with hydrogen, and we're just looking at the radii of these atoms in order of atomic number. And so we do see some patterns here, right? The radius jumps up and comes down and jumps up and comes down, and it keeps doing that. That's a periodic property. If we look at the ones on the bottom here, the smallest ones at each of these dips in this thing, these are all noble gases. They're in group 1A, 8A. And so if we look at the trend from helium through all of them to xenon, we see that as we're going down the column, the atoms are getting larger, right? And if we look at the high points here, these are the alkali metals, lithium, sodium, potassium, rubidium, cesium. Again, there's that trend that as we go down that period, the radii is getting longer, the atoms getting larger. This trend is intuitively reasonable, right? Because you compare lithium to sodium. Well, lithium has 3 electrons and 3 protons. Sodium has 11 electrons and 11 protons. You could probably ask a kindergartner which one's going to be bigger, and they'll say, well, the one that has more pieces, right? You don't need to know very much for that. So that one makes sense. We can explain it with quantum mechanics by saying that the principal quantum number n is increasing, so the valence shell is farther from the nucleus. So lithium's valence electrons are in the 2nd level, sodium's in the 3rd, potassium 4th, 5th, and 6th. The principal energy levels are getting larger and larger as the n gets larger. You kind of think of it this way with the hotel, that an approximate correlation with the radius of the atom would be the distance from the hotel front desk to the people staying in the highest floor. Not the empty floors, but where the people are. So if you have people staying in the 3rd floor, that's a longer distance than if you only have people staying on the 2nd floor. If you have people staying on the 6th floor, that's even farther. And so the 6th level is a larger level. It's higher in energy, and it's also physically larger. So because the valence electrons here are in a higher energy level, they are larger. This is larger than rubidium and anything below. But then we see this weird trend. You know, it's like, well, if it goes by numbers of protons or something, then why isn't this just a nice straight line, or even just kind of a wobbly line that's a general trend up? But it goes up and then it comes way back down, it goes way up and comes way back down. So I will attempt to explain that to you. Here we have there's a name for this kind of graph. It's 3-dimensional, it's not just a bar graph. Maybe it's a 3-dimensional bar graph. I don't know. But the heights of these little columns correspond to the value. So here on this axis we're looking at picometers in radius, and we've got the whole periodic table here. So we see helium, lithium, sodium, potassium, rubidium getting bigger. Any of these columns, you can see they're getting bigger as you go down. But then as we go across, say lithium, beryllium, boron, carbon, nitrogen, etc., the atoms are getting smaller. That is not intuitive. Neon has more protons and more electrons than lithium. Shouldn't it be bigger? Well, you would think. But we have aspects of shielding again. So multi-electron systems, we've got electrons that are simultaneously attracted to the nucleus but also repelled by other electrons. So the outer electrons get shielded from the nucleus by the core electrons. And we collectively came up with the analogy that the nucleus is a celebrity and the core electrons are, a group of people crowded around them because, everybody wants to see the celebrity. And then the valence electrons are the guys on the outside of the crowd, right? And so they can't see the celebrity as well because the people in the middle there, the inner core, are in the way, right? So shielding causes those outer electrons to not experience the full charge, the full strength of the nucleus. So again, here's an example with lithium. So here we have the nucleus. Here are the 2 core electrons, and nothing is really standing in their way. They're just getting the full glory of the positive 3 charge on the nucleus. But this valence electron out on the 2nd level, these 1s electrons are a little closer, and so they're obscuring the view that this electron has for the nucleus. And so we can estimate the effective nuclear charge as the charge on the nucleus minus the number of core electrons. And so effectively, this valence electron is seeing a positive 1 charge. It's attracted to the nucleus, but not as strongly as these core electrons. There is a more precise equation for estimating effective nuclear charge, but this is good enough for us. The effective nuclear charge is the actual nuclear charge, the atomic number, minus the number of core electrons. So it's shielded by the core electrons, so you subtract the number of core electrons. Now, do valence electrons shield each other? They do, but it's a very small contribution, so we're going to ignore it, right? Love it when you can ignore difficult things. So what are the effective nuclear charges of nitrogen and argon? Well, we need to look at either electron configuration or orbital diagrams for these. Let's go with electron configurations. So for nitrogen, the electron configuration would be 1s2, 2s2, 2p3. Right? Here we have the valence electrons, and these are the core electrons. So if we're trying to calculate the effective nuclear charge, Z effective is going to equal the actual nuclear charge. So for nitrogen, that's 7, right? It's element number 7. It's got 7 protons. 7, and then we're going to subtract the core electrons. These are the core electrons. These are the valence electrons. The core electrons are all the electrons that are not valence electrons. So 7 minus 2 is 5. So those valence electrons are seeing a plus 5. Yes? Yeah, can we just look at the number of valence electrons or the group number? Yes, it does correspond to that for the main group elements. It's helpful, though, to understand why. And then it says to do argon. Okay, well, argon, 1s2, 2s2, 2p6, 3s2, 3p6, right? The valence electrons are in this highest level, the 3rd floor of the hotel. The core electrons are everything below that. They get in the way. So, core electrons, valence electrons. The effective nuclear charge is going to be the actual nuclear charge. So argon has 18 protons in its nucleus. So the actual nuclear charge is 18 minus the number of core electrons. How many core electrons are there? 2 plus 2 plus 6 is 10. So subtract 10. And so this has an effective nuclear charge of 8, which does correspond to the number of valence electrons. That works for the main group elements. Definitely for the smaller ones.
And the effective charge is only the charge, how it's affecting the outer.
Yeah, the effective nuclear charge is, we're looking at what kind of an attractive force are the outside electrons experiencing. So moving down a column, the radius is getting larger because we're getting into larger and larger principal quantum numbers. And each of those levels has larger orbitals, and so we're going to have a larger atom. Moving across a period, here's the explanation. Well, the effective nuclear charge is increasing as we go across a period, but the N is staying the same. So N tells us a rough distance from the nucleus, and then we can look at the effective nuclear charge. So let's see if I can illustrate this. So here's lithium. 2 core electrons, 1 valence electron. And then I'm not going to go over too far because I don't want to draw too many electrons. We'll just go over to nitrogen. So nitrogen is +7, and it also has 2 core electrons and 1, 2, 3, 4, 5 valence electrons. This is where it can be helpful to think about the Bohr model, because in the Bohr model it would look like this, and here's n equals 1. The first orbit is the smallest, and the second orbit is larger. And so here we have the first orbit and the second orbit. And so that's kind of like a starting point. But then we have to look at what is the potential energy of the attraction with the nucleus. So for lithium, the effective nuclear charge is 1. And for nitrogen, the effective nuclear charge is 5, right? And we've looked at Coulomb's law. The potential energy, the amount of attraction, is proportional to Q1 times Q2 divided by R. So here I have a -1 electron attracted, seeing an effective charge of +1. Here I have an electron with a -1 charge, seeing an effective charge of +5. So for nitrogen, Q1 times Q2, we have -1, -1 times +5, and so that's the potential energy is -5. Here, for 1 electron, it's experiencing a +1 from the nucleus, and so we have the energy is -1. There's more attractive force for the nitrogen. That attraction is going to pull the electrons in a bit. And that is why, as we go across a period, because the effective nuclear charge is increasing, the electrons get pulled in a little bit further with each successive element. Any questions? What about the transition elements? Well, we still see the size increasing as we go down a column. But when we look going across a period, things are much less predictable. And so we're just going to go for the general idea here, which is roughly the same size across the D block. There is some difference, but the difference is much less than for the main group elements. It's not as predictable. Here we have the valence shell is those 2 s electrons. I need a periodic table. There it is. So as we're going across the transition elements here and adding in electrons, we're adding electrons to the 3D sublevel. So we're adding core electrons, not valence electrons. We're also adding a proton as we go across, but since we're adding a proton and a core electron, the effective nuclear charge is the same across all of those transition metals. So their sizes are roughly the same. If we go back to our graph, here are the transition elements for period 4 and for period 5. And you say, well, those aren't the same. Yeah, but they're roughly the same. It kind of goes down and then flattens out. I mean, these guys are definitely really close to the same, right? And so we don't want to remember any more detail than that, so we'll go with, yeah, those are about the same. Good enough, right? Here, looking at these numbers, come on. We see that they do go down, but then they come back up again, and so we're just going to go with roughly the same. So these are the sorts of questions that you should be able to answer. This could show up on an exam. On the basis of periodic trends, choose the larger atom in each pair if possible. So we have two elements. There's two choices there, but then we can also say it isn't possible to tell on the basis of periodic trends. So we need a periodic table to do this. That's why I added one to the slides here. So the first one's asking about tin or iodine. So we got to find these on the periodic table. Here's tin, and here's iodine. And we look at, well, how are they positioned relative to each other? They're in the same period. So then we have to think, well, what's the trend? As I'm going across this period, are they getting bigger or smaller? They're getting smaller. It's like, okay, it was the opposite of what I thought. Or you could think about the effective nuclear charge, and they're getting pulled in tighter and tighter. So which of these is going to be bigger? The tin, right? Because we're getting smaller as we go across, so tin is bigger and iodine is smaller. Let's look at GE and PO. G and Po. Germanium and polonium. Cool thing is you don't need to know their names. All you have to do is find the symbols on the periodic table. So there they are. Now this one's on the diagonal, so a little more complicated. Let's go for the easy trend first, right? So going down, they get bigger, right? That's the one that makes sense. Going down, they get bigger, so that's a vote for polonium being bigger. But when we go across, they get smaller, and so that's a vote for germanium being bigger. So these two trends are opposing each other. If I was forced to choose, I'd give more weight to the going down trend, and I'd pick polonium as being larger. But on an exam, the correct answer here would most likely be it's not possible to tell.
It's the same amount of distance, right? Because there are 3 down and 3 across. It's almost like it was 40.
Yeah, if you were looking at like rubidium versus polonium,
Right.
then you're like, okay, well, this distance is huge, so there's probably more effect there. I'm going to predict that the rubidium's bigger. Or if we're looking at nitrogen and polonium, you know, where we're going over a smidge and we're going down a lot. But here we're going over 3 and we're going down 3. And it's like, could go either way. Maybe they're the same size. That's possible too. Okay, chromium or tungsten, CR or W. Well, I gotta find these guys. W, where'd you go? There you are. We are careful about the questions we ask you here, because it would not be fair, well, I guess you could say it's not possible. If I asked you about 2 transition metals in the same period, you're like, I don't know, you said they were the same. But these are 2 transition metals in the same group, but different periods. So which one's bigger? The one at the bottom, right? The W, tungsten. Any questions?
So when it's a little uncertain, you tend to give more value to the downward trend and increasing size over the...
I would tend to give more value to that because you're going into larger subshells,
Yeah.
or I mean larger levels. But that's only if I'm forced to choose. If I had to choose germanium or polonium, it was multiple choice and there wasn't an option for not possible. Like, that's what I do. But I won't do that to you on an exam. I don't know about the homework. Okay.
So, just like for a basic understanding of like the size chart,
Mm-hmm.
top smallest, bottom largest, and then this side smaller, this side bigger.
Opposite. So as we go across, we're getting smaller. As we go down, getting bigger.
Is it more attractive from left to right?
Yeah, so as we're going across here, we're putting electrons in the same floor of the hotel. So they're roughly the same distance from the nucleus. But the nucleus has more and more charge, and so they get pulled in. It's a better celebrity in the middle there. Sexier, yeah. Going down, we're putting electrons into higher floors on the hotel, so obviously they're going to be further away. So we're going to be learning about several different periodic trends. And this is one that I think is very, very helpful to be able to reason out, to think about. Because most of the rest of them, if you know which is bigger, which of the two things you're comparing is a larger atom, then you can just figure out based on that, oh, is this trend larger or smaller? So I'd really encourage you to get this atomic size thing straight. Okay? And rote memorization can work for this, but again, it's two pairs of things. Going across, bigger or smaller. Going down, bigger or smaller. So easy to get them mixed up.